Lecture 4 for the Morphosis class on the Ethereum developer course for the One Hive community. We are gonna see today how to use the Ethers.js library and write some tests with it. Um, yeah, so far we've been talking about more low-level concepts and trying to understand the fundamentals of blockchain technology and development in blockchain. And now we are starting to do more practical work into the high-level libraries and tooling that we have at our disposal. And one of those libraries is Ethers.js, and that is one of the most powerful libraries that we have available right now. And what it does, it abstract for us a lot of the low-level concept that we have seen so far, and give it to us in a much more developer friendly and with a nicer API for us to interact with. So to start with, we will see what are the most important concepts in Ethers, and those are the concept of a provider, a signer, and a contract. And the concept of a provider is something that we've been working on in previous lectures. And what it is the abstraction of a Ethereum node in the and how to interact with it. And as you remember, we saw an experiment with the JSON RPC, and that sorry, and that was the low level way of interact with a Ethereum node. So what Ether does is abstract that concept of interacting with a node in this object called a provider. And what a provider does is most of the things that we've seen so far with the JSON RPC, but also includes some other nice features and a much better API for us to interact with the blockchain and the different Ethereum nodes, and have different kinds of providers that are useful for different things. So, for example, we will be seeing, but using MetaMask or using a JSON RPC or whatever. But then the next concept is the concept of a signer, and a signer is this abstraction as well that ethers give us of having all the necessary things to that are part of a wallet and that allow us to sign messages, to send transaction, to actually write information into the blockchain. No, so if you remember in the previous lecture we talked about the the key pair and the private key and how that was generated, and most of all that concepts are encapsulated in the signer in Ethers, and give us a really nice API for us to use all that functionality in our test or in our deployment scripts or in whatever we need for the using the Ethers library. No. Finally, the last concept that Ethers handle in a high level is the concept of a contract. And this contract object is also an abstraction of what a contract represent in the blockchain. And if you remember, before once we deployed a contract, we were getting the ABI and the bytecode, and those things are like the key elements that Ethers also will be using to generate this contract object and give us a really nice API for us to interact with the contract without having to think too much about the encoding or decoding or of bytecode and of hexadecimal arguments or whatever, and instead trying to um, talk with the contract in a much more high level language and using a classical JavaScript object. So now, then also there is a lot of utilities that Ethers has and use internally, but also exposed for us. And those are probably leave for other video or later for you to investigate on your own. But those are powerful as well to help, for example, have access to different hash function or big number data and encoding and decoding it that might be useful in some particular use case. So yeah, this library is really feature complete for you to handle everything related to Web3 development. So now we are gonna start seeing some examples of using the Ethers library in production. So first of all, I have here a hard hat script to demo a few of the things that are happening. And if you can see here, we are using the hard hat runtime environment and connecting to the Ethers library directly. And this is possible because we are using we first of all install the package JSON. First of all, we install the hard hat Ethers package, and then we in the hard hat config we import it, so we will able to use it in our code everywhere. So that's why we have this here, and this is not exactly the everything that is in the Ethers library. Is everything that is in the Ethers library, but also there are some small handlers that hard hat give us to improve the experience of using Ethers inside hard hat. But everything that is in Ethers will be available for us. So first of all, I put here how we can create, use a provider and call a provider, and this is the one of the usual ways of using a provider is directly call the get default provider function, and this will get the provider by default that is connected to connect to, and that by default will be mainnet. But if we provide a network can have for example, in Ethers, a network object will have the following format. We will have a chain ID, a name, and an optional ENS if you want to use your own ENS. But if you provide all that to the default provider, you will be able to connect to other Ethereum node that is, and this will be the way. And then we also, in this case, we are gonna be using for this demo the provider that is configured by default when we run a script in hard hat. And if we are running without specifying a network, we will be running the hard hat chain, the hard hat network directly. But if we provide a network, we will be handling, I don't know, the Infura in Rinkeby or whatever other XDAI using some XDAI node, and that will be this for the hard hat. But in our case, we are probably do it directly with the hard hat local chain that we will be running. So yeah, we can start doing some debugging, and let me tool so we will be able to see it better. But if we run this demo in here, we'll be connecting to the let me see, let's run this, and this is a configuration that I made for debug this, and what it does is just run the demo connected to localhost. And yeah, sorry, I forgot, I will also need to run a local chain, otherwise we will not be able to connect hard hat node. So let's run this again. So now we will have in our provider we'll have the local hard hat network connected. So now, and in the default provider, we will have probably the homestead or mainnet address, and that's the network. And we will have the default mainnet node for us to use. And in this case, we will have the local hard hat network that we are using. And that will be two providers that we have at our disposal right now. So to show you a few of the methods that we can call in the hard hat, we'll first, let me show you. First, we will have we can use, for example, the get balance that is similar to the get balance that we were using in JSON RPC. So if we call this, we'll get in, what? 1 second. We are getting, in this case, the balance. So we are calling the balance, and we are getting, we are formatting with this util that it provides us to give us a nice, because this is returned in hexadecimal, as we are using it directly from the provider, and we get in here the balance of the hard hat first test account, and that's almost 10,000. Then we will have a example. We can call, for example, get code to get the bytecode of a specific address. For example, this address is an address that I deployed in the local network to show you this. So now if we go to the next, put a breakpoint and go to the next, we will have all the bytecode displayed, and that's how we get it with the address directly. We can also call, for example, the get transaction count from a specific address, and we will get the nonce. And that's really nice because that's sometimes needed when we want to know how many transactions are sent so far and put it in the transaction, the nonce. And this case is 3 for this address, the test address. Then we are also able to use ENS methods, and these are some syntax sugar that Ethers provide us for us to interact with ENS in a much easier way. So right now, if you notice, we are actually using the mainnet provider, because in local we don't have a ENS set up in our chain. So that's why we are using the now we are talking with the mainnet node, and we are using this lookup address. That what we do is trying to get the name related to this address, and let's see if that works. Okay, we didn't get for that address lookup, not sure why, but yeah. But the other one that we can, this will do is trying to get us the die. Yeah, if we do it the other way, let's try to run it again afterwards. But in this case, we are calling the result name, and given a ENS name in this with this format, we will get, for example, for this case, the mainnet die address. So if that works, we will get the address, and this is the address of the ENS. And to test the other way around, let's put this address here. Let's run it again and put a breakpoint in here. So yeah, no, it's not resolving. Not sure why. It's not looking up the address. Maybe it's working in another way that I'm not aware. But yeah, this is the, no worries. Now, the other thing that I wanted to show you is the signer. That this is the other concept that we've been talking, and how we are getting the signer is giving a provider we can get the signer directly. We have the signing method that allow us to use a signer to interact with the blockchain, and now we will be using this for sign a message, for example, as we did in previous lectures. And as we can see, we will get a signed message with a hash of the message we are signing. Then we will be able also to create a transaction request object and send that transaction using the signer as well. And in Ether, we have three kinds of transaction objects. We have the transaction request, we have the transaction response, and the transaction receipt. Each of us is what it is in different parts, in different times in the transaction life cycle. So when we create the transaction, we will be having a what is called transaction request in Ethers, and that is the bare bones transaction. Once we send the transaction to the blockchain, we will get back a transaction response object, and as we can see here, we have a transaction for a claim of the contract we will be interacting. We will be getting a transaction response that we will see now, and the transaction response has the following structure: is the usual transaction that we get back from a provider of this JSON RPC method, and it will have some better handling of a big number, for example, and some better hex encoding for us that Ethers is doing to make it easy to understand things like chain ID, for example. Instead of having it as a hex number, it's converted into a number, the same with the block and other values. Or for example, the gas limit, that is a really big number, we get a big number already. So this makes it more easy to handle. And once we have the transaction response, we can wait for this to be mined in the blockchain. Of course, as we are in a local network, we are not we will be getting mined right away, but this is in general that we need to wait for the transaction to be mined. And once this wait finish, we get the transaction receipt that has already all the information related to our transaction. And once we have that, we can be sure that the transaction is included in the history of the blockchain, and we can interact with the contract if we are doing a deployment or do some other stuff now with the information about it. And in this case, we are also getting the logs with information about it, about the events that were emitted. And yeah, continuing to do with the example, we have the third kind of concept that we will be talking about in Ethers, and it is the contract. And as we were saying, the contract is like this abstraction for Ethers to provide us to interact with. And in this case, we are going to be using a DAI contract, creating a DAI contract from mainnet. So we'll be using directly the ENS name of like we were doing before. We'll be getting this DAI ABI, and as we are only interested in the name of method and the symbol, we'll be getting this in this way. And this is the what is called the human readable ABI. And instead of having this syntax that we saw in previous, as we can check right now from for example, for the RC20, we'll have this. This is the usual ABI format with all these ugly formatted of different things and methods or events or functions or whatever. By this way, Ethers also allowed to have this other format, like human readable format, that this is actually almost the same as the function method. For example, in the case of this RC20, we can just get this, and this will be like the human readable ABI for interacting with the set balance. So in this case, we can also provide only a subset of the ABI methods or events that we are interested. So in this case, we are only interested in the name, and even more, we can only put the symbol because we are just using the symbol to interact with the contract. And then we can create a new contract with the iter's method to create a new contract. We will provide the address, we will provide the API, and the default provider, that is the one connect to mainnet, and we will be getting this contract object to interact with. So now we have this contract object with all the information, and we can just interact with it to get the die symbol. So now we can get the die symbol, as we can see. And this is directly from mainnet. And now to the final example, we'll be using the contract factory. This is the way we can deploy contracts in ethers. And how we will be doing is first we'll be using getting the artifact from the ethers library. We'll be doing it this way: the hard hat runtime environment, that artifact, that read artifact, and we'll be getting this test ERC20 contract from our compiled codes, and this will get it. We will get this ERC20 artifact object that will have all the information we need to interact with to create a new object, create a new contract object. And as we can see, we have all the API, we have the bytecode and more things. And with that, we'll be creating a factory using the API and the bytecode. And this factory will be created with the contract factory method from ethers. And once we have the factory, we can call a different method to, for example, deploy or connect to the factory. But the most important will be to actually deploy the contract. And as we can see, if we stop right here, we'll be having a deployment done, and we can check yeah. Oh, sorry. I think I stopped the execution actually. Let's do it again. Cool. We might need to actually, we might get an error because we already claimed. So let me restart the hard hat local chain and run this again. And now we will have everything correctly, if I'm not wrong. And we'll be having the ERC20 factory here when this is processed. So we will have the factory. Now we'll be deploying the ERC20, and actually we got an error, send transaction of null. That's because factory. Okay, but yeah, the idea here is that if we deploy this ERC20, we will be able also to interact with it. And yeah, with that, the demo was to showcase all that. And now the idea is to continue with a more specific example of how to test an actual code in using ethers. And what we will be testing is the Merkle distributor contract. And this is a simple but quite interesting contract that, let me put this in the middle to make it easy for us to show. So this is the Merkle distributor contract. This is the one that Uniswap used for their airdrop. And this is really interesting contract because it has a quite a simple logic, but anyway, quite powerful. And in general lines, what it does is when we create a new Merkle distributor contract, we are providing a token that will be distributing and a Merkle root. This Merkle root is a hash of all the verifications that need all the addresses that will have an IDO, and with this hash we will be able to prove that everyone that wants to distribute an airdrop is in the actual airdrop, so we can verify that using this Merkle proof that provides Sepet, and I will for you to understand. Then the most important function, claim function, and what it does is require that there is no claim before this data in the claim, like in this the index of the address that is claiming, the address itself that is claiming, the amount that is claiming, and all the proof that they will providing for us to verify that they are actually in the verification tree of claims. So with all that, we will be doing verification using this proof contract that OpenZeppelin has for doing this kind of verifications. And if everything goes okay, we'll be able to say okay, this is a person that has an IDRO for them, and we will be setting that as a claim for that address and index, and we'll be saying that we'll be setting the tokens that we have in the distributor contract to the address that is claiming, and finally we will be emitting an event claim to register that. So this is all the contract for that. And now what we will be doing is start to write a test for the contract. And do that, we'll be using the library. We'll meter number, which I library to write test and provide certain checks that will have to make sure everything works as we expect for our contract. So to start, let's create a describe method. It's a method use framework test, and what it does is just a way to describe what we are going to do. So we'll be giving a and what we're doing, this is the syntax of test writing mock, and this callback function is everything that we will be doing here. So inside here, what we would like to set up a few global functions for us to have at our once we start writing the test. So we will have two wallets of kind signer with address. This will be a signer, and also we'll have the address of the wallet. So once we have, for example, wallet that address, we will be able to do that, or we'll be able to do sign message or whatever, because and we will also need like a token. It will be a test ERC20 token. And as you can see here, we are actually using this interface that is getting from type chain. And as we can see, this type chain is a definition for contracts definition. The only thing we need to install this type chain hash, include it in our config like this. Every time we do like a hash compile, we also type generation as part of that task. and that will create this type folder for every contract we have in our repository. What is really great for us to can, for example, know that we can call allowance or approve or whatever that a token has and make it easy to prevent some errors. So things that we need are like ERC20 factory, and that will be like a test ERC20 factory. And we are gonna also need a distributor factory to create Merkle distributor contracts factories. So we saw global variables. Now we are going to use this method before, allow us to execute certain actions before everything else. And what we will be doing here is set up the wallet using the Ether's get signers. This is a function that Ether has to get every signer that is connected to the provider. So in this case, by default, we will be connecting to the localhost chain, the hard chain, and we will be attached to that. Those will be the accounts signer, Ether signer. If using MetaMask, we will get every MetaMask account that is connected with their own signer as well. Also, is a 20 factory deployed, and we are going to use these ears that get contract factory. And here we are using this get contract factory that is not actually a method in ethers, but it's this syntax that had a package, the hard ethers package that we installed, this one, provide for us. And what this does is allow include a extra layer of logic on top of ethers to make it easy to create a factory, because we already have every artifact in here and only providing the name. Here we can just say test ERC20, and we already get that factory without any more information than the name, because everything else can be derived by Hardhat from this artifact, because he already knows that if the name is test ERC20, he already have here the ABI and the bytecode that are the things that he needs. So that's a really easy way for us to do it. And now we can, yeah, this is test ERC20 factory, like we were saying, and this is how we are creating this factory. And we will be similar by the Merkle distributor. Merkle distributor contract, and this will be a Merkle distributor factory. So now will be this is everything we want to do before every other task, and then we will also want to do before each test that we will be running. We want to deploy a token, and we will be doing this similar structure, just describing what we are doing, and we will be setting up the token in this way. Await ERC20 factory that deploy, and we will be putting all the token, ERC token test, provide that token name, this token symbol, and the as a start just 0 will be the 0 tokens at the start. So now with this will be running before each test. So it's only running once before every test. So now we are actually starting to the actual test. We call to the token, testing that. So we are first test with if methods. And what we will be testing is that once we create this Merkle distributor, we want to make sure that both the token Merkle root that are public variables are correctly, but to make sure everything works as expected. So we will say that we want this to return the token address. And this will be also the same syntax, I think. And we'll be doing, okay, first of all, we'll be creating a distributor using the distributor. Here we'll be providing, distribution deploy. And what we need to provide here is both the token address. If you remember, the two things for the contractors are the token address and the Merkle root. And for the Merkle root, we need to provide a hash of the trees, but as we are just deploying a test without any error, we will be just doing an empty hash, and that can be get with this hash 0 constant. And as we can see, this like value. And with this, we'll be using now the assertion library we were discussing before to prove that things are we expect it to be. So we'll be using assertion from Chai. We will be saying we want to the distributor that token, we want this value to equal the token that address. So if this is I forgot this one here. So what we are testing here is that once we deploy the actual contract, the Merkle distributor contract, we provide the token address and the 0 value for the hash, the Merkle root. We will expect the token inside this variable to be the token address if everything goes correctly. So now we can go here and say, okay, npx had test Merkle distributor test. We only want to run this test. So we will say that in this way. This will run everything we have so far. And as we can see, this is the way that Mocha displays the information. We will have the description here, like we say, describe Merkle distributor. We will have all this setup done, this only once, and we will have here the token deploy once. And once we reach our actual test, we say, okay, we want to test this token, describe, that's why it's here saying token. And finally, when we say date, we are actually testing this return the token address. As this is a value, this value is true, we are getting a green check mark to say this is as we expected. Now we can continue with a similar test, but now instead we can check, for example, the Merkle root value, and this will be quite be deep in the way. We get instead the zero root. Here instead we'll say the Merkle root, and here we'll say again the constant to check with the either constant, and that's it. That's it. Again, this will have a new test for the Merkle root. So the index to test most relevant sections of the smart contract, that is the claim function. So in here we have several things that are important to test, and trying to test are is to claim an error one and try to claim getting this drop already. Also try a claim successful both and getting the tokens distributed to the address that was doing the claim. And finally, we also want to prove that if the verification has wrong proof or wrong data, this is also gonna fail in the verification process with a so to doing this. Yeah, right here, but now I'm gonna call the claim and we'll be saying sorry that we want this in this way. And for the claim method, first of all, we'll be testing that let's fails for empty proof, for example. And to do that, let's deploy again a distributor with this same pattern, and then try to use a wait, expect distributor that claim. Let's call out the claim function with just mock values like 0. Let's put the address. This will be the index that we'll be claiming, the wallet the address of the claimant. Let's put a 10 value and just proof like what we were trying to accomplish, like just this array of proof to be empty. This call that a Merkle proof. And now this should be reverted with a specific message reason, and that message will be Merkle distributor invalid proof. So let's put this here, and now if we run the test again, this is filling. What we did here is again this deployed the Merkle distributor again. In this case, called the name some wallet and index, even though the distributor has not, as we get in, we will revert. This is invalid proof. To go with an actual data. To account of claims. So this will be more interesting because claims in this new distributor contract. Let's create a global distributor to use in every test on. And let's also a balance tree. And this balance tree is a function, is a class that is defined in each app like this. And each has three very uh, expected, and from that we'll be able to get the proof. We participate also the root of the proof, so we'll be using to construct distributor and to showcase the much more once we write it. So what we'll be doing is before each test that we write, distributor that we'll be using for the test. And now that will be do first of all create the tree, and we'll be doing it with the balance tree, new balance tree, creating this here. And no worries to understand everything here, but the way we will be constructing is with this format. Let me copy. This will be an array of objects, and each object will have an account element with the address that will be getting an airdrop and the amount that we will be getting that address for that airdrop. So here we are two accounts. One wallet we will be getting 100 tokens, and the second one. And once we have we will be able to now call the distributor factory again, but now with more actual data. We'll be also using the same token again that we deployed before every, so getting a new one every time. And this for the root, actually using the tree hex. In this case, we have this getting a hex root that is a hash of every balance tree. I'll show you too once we get the test done. And finally, we want to use this set balance method that we have in the test ERC20 that we define. And this set balance allow us to set a balance for whatever address, set an amount. And this is really useful for tests because it allows us to set whatever balance. And what we would like to set here is for this distributor that was deployed, we want to set them 201 tokens to have enough to pay for every airdrop, in this case 201. So now we have for these two accounts tree example, we have everything set up. So now we can go ahead and start writing the test. So let's put it. So the first things we want to test is, let's do a successful claim. and that the same syntax that we were doing before. And let's, first of all, we are going to need the proof of the address of the for the account 0. And to get the proof, we will be using the tree that we define here, and we will use the get proof method that we have. And what we need to provide is the index, that in this case is the index 0. We need to provide the address of that, how much and how much is the amount in this case, the number 0. With all that, the tree will get us the proof that we need, and then we can now call the expect function to get the distributor that claim now with actual data, like, so we will have the index 0, the wallet address, the big number, the amount, and finally the proof that we'll be using. And with everything, with all that, we will be able to actually claim, because all this data is the right one. And so what we will expect to happen here is to emit, to have an event from the distributor contract that is to index 0, wallet address, and the big number from 100. So now, as we can see, this is the claim event that we will be testing. And as we can see, it's the index, the account, and the amount. So if everything works as we expect, this will be what it will happen. And the other thing that we want to do here is to make sure that the balance of the address of this wallet 0 actually receive the token. So we will also testing that the token that balance of the wallet 0 address is equal to number to 100. So now both testing that the claim was correct, wallet address received the error that was corresponding to him. So let's go ahead and put a debugger statement here to start testing this. And yeah, successful claim here. Oh yeah, this is the version, the final version with test that, so you can check before afterward. But now I wanted, so let's do this. Oh yeah, let's stop this process and run this again. So now we will have here, as we can see, this is stopped here. So we will have all the global variables set up, and we can see the distributor, we can see the tree. But what I wanted to show is this get hex root. So if we see this hash, this part will allow us to verify that the proof that someone sent us, for example, in this case, the proof will be other hash that is to prove that the particular address has claim for that. So now with that, once again. And if everything was correct, we will have a successful claim. So as it seems, so far we have a test correctly. So now what other things we want to do is also test, for example, that the is claim sets correctly. So that will be, for example, that once we do a claim, we want to also make sure that this set claims. We will say set here. Now, once again, we will be using the first proof here. And now what we want to call the isClaim method for 0. We will expect this to be false because this was not claimed. This address didn't claim yet. As we can say here, the isClaim is going to return a boolean depending on if this index was claimed. But now once we run this claim, as we can say here, for example, we will run this claim again, and then what we expect is this to change from true to false, from false to true, because it was already claimed, and that is everything we want to test actually for this case. Let's go ahead and check if that's the case. Yeah, this is also set correctly. And as you can see, yeah, now we can also test this check how to claim. So let's go ahead and let's get proof. And in this case, we also do but the second what we want to do is that if in the second case that you create a claim for this, there actually expect to be reversed with error of Mercury claim. This error, and if everything works as we expect, this will also run. So yeah, this is as well. So now we have everything that we wanted to test, and there are several things testing, but this is, I think, quite enough for now. And I will be, like I mentioned, leaving a final the Merkle distributor test with several more tests that can be done, and also more large trees that are able to provide more real case examples of how this claim might work. To final thing, I wanted to show some extra to improve this our test to and make it more valuable. So for first the soil coverage package, and what we need to do then is comment have it a new coverage task in hard hat that we can use. So I will do this, and what we'll be doing this is running a few things, uh, compiling the code, doing several things under the hood that the library does. This you can skip this because these are all the final tests that I skipped, so you don't affect our results. And finally, with all the tests that we write, are considered to create this information for us. This is a measure of all the that our tests are handling in the contract. See here, we are seeing right in this coverage folder, and let me bring this coverage information. And this is the format called the coverage. Contract distributor will have all the information about coverage because we test every slide. To give an example of this, if I, for example, instead of we just try the modify or this last, and we this again, what will happen is that we'll have much less coverage in our code because, as we can see now, if we update here, we will have several sections of the code that we didn't go by, and we actually create a test for and make sure everything is working as we expect. So it's a really good tool for us to make sure everything that we write is actually covered and considered. So let's leave this. And yeah, the only thing I wanted to show you is an extra tool that we can use as well, that is hard hat gas reporter. And in this case, we are also just installing this package and having this line in our like hard hat reporter comment that we'll be able to run our test, and those tests will be including gas information. So as we can see, now our tests are data that related to the contract. Use this information to have, for example, all the methods, how much gas they will be spending, the deployments, how much will be costing in the for the Merkle distributor or for the test ERC20, for example. And yeah, this is really super relevant when once we start writing production code and sharing it with our users. So yeah, super useful to have it. And yeah, that's mostly everything that I have for today. The only thing that I want to also mention is that we can automate, for example, this solidity coverage and test with GitHub overflows. And this this is an advanced topic, but really relevant, that with GitHub you can create these workflows files that allow you to automate, for example, that every time you commit some code, you can run several things. And in this case, I'm running, for example, the compilation, the installation of the packages, and finally running the test. And in this case, the coverage that is creating a coverage information for me and uploading to this code called library that is really cool, because if we can see this code is this like similar to what we saw, but it's Twitter line is updated with every commit that we do. So it's the relevant team development, but way to automate things. But yeah, that's everything that I want to show you today. I hope it was useful, and see you next week.